Hey guys, welcome to our video on Project 2001 High Performance Machine Learning. In this video, we will be talking about our project. Our team include Oran from Technical University of Istanbul, Mohammad Omer from University of Manchester, and Michael Pitoniak, who is our project mentor. So let's see what machine learning is. It is a computer algorithm that gives system an ability to automatically learn from data without being explicitly programmed. The algorithm uses data as an input to predict new output. Machine learning is a subset of artificial intelligence. The data is labeled and fed into machine learning algorithm. The algorithm finds a pattern for each class of objects and then predicts the class of object on an example it has never seen before. Machine learning needs big data. Big data is a term used to describe collection of data in huge volume. Companies like New York Stock Exchange, airline companies, Facebook stores hundreds of terabytes of data every day, which we refer as big data. The reason why machine learning is so popular because it can perform tasks beyond the scope of human beings, such as identifying patterns from tons of data, automate a process, efficiently handle data, and improve it. Big companies like Google, Twitter, Facebook, Pinterest, IBM, Grammarly, etc. are using machine learning for their daily operation. In our project, we are working on decision tree classifier, a type of machine learning algorithm. Decision tree is a binary algorithm used for both regression and classification problems. We are using the cart type of decision tree. In this algorithm, predictions are made as we move from the root to the leaves of the tree. Each node is assigned with a Gini impurity, which describes the purity of the node. The aim is to find optimal distribution feature and a threshold value such that Gini impurity is minimized. The algorithm stops when the maximum depth is reached. Here you can see as we move down to the leaves, Gini impurity decreases. Let's assume we have 5 samples or objects distributed such that 2 are of classroom 1, 2 of classroom 2, 1 of classroom 3, and none of classroom 4. In that case, the Gini impurity can be computed as follows, where n is the number of samples and p, which is a function of k, is fraction of samples in each class. Next, we will be discussing in more detail how the algorithm works.
The idea behind the CART algorithm is finding the optimal feature and threshold couple, minimizing the Gini index by testing all possible splits. For finding the best splits, firstly, the program starts with a feature set and iterate through the sorted feature values for possible thresholds. While doing this, it keeps track of number of samples per class on the left and right. It applies the same procedure for each feature set. Finally, the program compares Gini indexes to find best couple for splitting. After that, all we have to do is to split each node recursively until the maximum depth is reached. It is obvious that higher number of feature and entries means that higher number of calculations. So, how can we improve the performance for big data? Of course, by parallelizing the algorithm. In the simplest sense, parallel computing is simultaneous use of multiple computing resources to solve a computational problem. MPI is one of the most popular tools to develop a parallel program. It is a standard message passing library for distributed memory systems. It allows creating separate processes on different computing units and establishing communication between each units. Our parallelization strategy is distributing features among the computing units. Each core is responsible for one or more feature set to calculate Gini index through the possible threshold values. Communication between cores are established by standard blocking send and receive commands. After each core finds the best threshold, they send this information to the master core 0. The master core compares them and broadcasts the best results to all the other cores. As it's seen on the plot, by this way great speed-up rates are obtained, but the communication overhead is inevitable. In an ideal world, workers can do their job independently, but in real world, synchronization is a must. There is no escape from communication overhead, so in reality, speed up is always less than the increase of the number of workers. What can be done more? Different parallelization tools can be used to further improve the performance. Gatsby is one of them. It is an API for development of scalable, asynchronous, and fault-tolerant parallel application. Detailed comparison of Gatsby and MPI parallelization can be found on blog page of Summer of HPC. Thanks for watching.